Look at the surface of a standard optical disc. From out here, it appears perfectly smooth, a pristine, mirror-like canvas. Yet that uniform reflection is actually the result of precision engineering on a scale the human eye simply cannot see. When optical media first arrived to hold standard definition video, the discs were massive. They measured 12 inches across, requiring record player-sized hardware. The industry eventually standardized around a much smaller, more efficient form factor. The compact disc shrank that footprint down to exactly 12 centimeters. This chart compares the capacity of that 12-centimeter form factor as it evolved. A standard CD holds 700 megabytes. A DVD increases that to 4.7 gigabytes, and a single-layer Blu Ray disc can hold 25 gigabytes, nearly 35 times more data than the CD. The physical canvas never grew. To fit that much more information onto the exact same surface area, engineers had to find a way to pack data into a microscopic geography. If we zoom down past the visible surface, straight to the physical data layer, the mirror finish disappears. In its place is a single, incredibly long spiral track, wound tightly around the center of the disc. Unlike a hard drive or a cassette, data here is not stored magnetically. It is etched into the material as a physical terrain. This diagram shows a microscopic cross-section of that track. The geography consists of two structural features: physical depressions called pits and elevated flat areas called lands. Every optical disc is a microscopic landscape, waiting to be illuminated. To read that terrain, we need specific hardware. This schematic shows the components of a standard drive: a motor, a laser, a focusing lens, and a photodiode sensor. The process begins when the motor spins the disc at high speed. Underneath, the laser fires a highly targeted beam of light through the lens, striking the spinning track. When the light strikes a flat land, it bounces off cleanly, reflecting a strong, solid beam straight back into the photodiode sensor. The sensor detects this bright reflection. The computer interprets that pulse of light as a binary 1. But when the laser hits a depression, a pit, the angled edges scatter the light away. The sensor receives no reflection, and the computer registers a binary 0. As the disc spins, the laser constantly alternates between hitting pits and lands. This rapid flashing, on-off, creates a constant stream of binary code. This is the underlying mechanism of all optical media, using the presence or absence of reflected light to build digital information. To fit 35 times more data onto that same 12-centimeter disc, those pits and lands must be scaled down and packed much closer together. But there is a physical limitation. An older CD drive uses an infrared laser. If you try to read incredibly tiny, densely packed pits with that laser, the beam's focal point is too wide. It spills over multiple features at once, making it impossible for the sensor to distinguish one bit from the next. The precision of a laser beam, how tight its focal point can get, is strictly dictated by its wavelength. The shorter the wavelength, the sharper the point. To extract more data from the same physical space, engineers had to use light with a smaller physical footprint. Here we see the first major shift. To build the DVD, engineers switched to a shorter wavelength red laser. Its tighter beam allowed them to shrink the data features and move the tracks closer together. Blu Ray represents the current limit of this approach. By moving to a blue-violet laser with an even shorter wavelength, the beam becomes razor-thin, allowing the pits to be shrunk to their smallest physical size yet. This precision also allows the laser to do more than just read the surface. The drive can shift its focal point to look through the top material, focusing on a deeper, secondary layer of data stacked vertically within the same disk. This microscopic engineering is what allowed high-definition video to fit onto a standard-sized disk, moving from the gigabytes of a DVD to the 25 or 50 gigabyte capacities used today. As the physical features on a disk shrink, the light used to read them must become more precise. The limits of digital storage are bound directly to the physics of light.